Hi friends, today we will understand how do computer algorithms recognize you and how do they actually generate applications or images that will represent exactly the questions which you have asked in the prompt. This video is the second video in the series where we understand various types of image generation and manipulation algorithms. So today we will understand about autoencoders and variational autoencoders and their working principle. What are autoencoders and why are they very important to the image generation space or a generative AI people? Autoencoders are very important because they offer you a unsupervised learning and a unsupervised approach of representing very complicated, large and wide number of images into a small set of featured representation. That too without the need of unlabeling them or without the need of labeling every image and the every feature. And even if you are doing the labeling, you only do it in a very small set of them. So building up that kind of a capabilities has made encoders very favorite for image generation, image understanding use cases. So how do the autoencoders work in principle? The first stage is called encoding, wherein which an image is encoded into something called as a bottleneck layer or a latent space layer with only representing the features of the image. So you pick that particular one and extract out the features and put those features in a representation in a matrix. What is the particular feature and how much percentage it is. So that is exactly what the autoencoders does. So when you do the encoding of that particular thing, what happens is it becomes very easy to represent complicated images or images with many objects or images that have many perspectives into a very small visualization. It will naturally compress the image, reduce the file sizes. It will also take the abstractions out of the image and be able to recognize the similarity between two given images in an unsupervised way, which is very helpful for the application. And then it can also search the contents of the application and representation in a very meaningful way. So not just encoding is enough. You what you do is in the autoencoders, you encode it to a bottleneck layer and you decompress it or reconstruct the bottleneck layer as using a decoder. So what is the use there? The use is in the process of encoding and decoding or reconstruction, you can get rid of the noise, you can get rid of the unwanted objects, you can get rid of many things which are not wanted, and you can actually enhance things which are wanted. So for that particular purpose, the encoder or the algorithm first have to understand what is in your image. So when you are specify using a prompt, it should understand what is in your image. So how it will do? It will do in this following way. So there is a encoder network. So it is not just one layer, whether it is a autoencoder or a variational autoencoder. There is a network which will take your image and then it passes through the several neurons or layers. Some are hidden layers and several neurons. Then all that will come in sit in a small latent space which contains a highly a representational feature representational perspective of your image. That is called latent space. Now, what is this exact latent space? The latent space is the representation of the features of your image. Okay. We will see example now. in the upcoming slides. After this is there, you can actually go ahead, apply to a decoder and generate the same in the style you want. Okay. Let us take example and understand what is a latent space. This example I am bringing up from a 1,000-year-old Sanskrit poet. Okay. And this is from Krishna Karnamrtam. Krishna Karnamrtam. So in this particular, poetic story, what he says is describing Krishna. He says, Kasturi tilakam on the forehead, and on the chest you have a diamond adornation, and then on the nose you have a nose pin that is glowing. In the hands he is having a flute, like playing pose, and with the hands you have got hand anklets. So that's what he specifies in hardly 15-20 words. But when 1,000 years later a autoencoder based model generates, it generates exactly the representational scenario because it knows the features, and those features are deconstructed using a deconstructed using a decoder. So now, representing a human, how he looks, what he looks, in a very small words, in a very small feature based activation, activatable features based thing is called latent space representation. This representation is seen in many literatures, in, in terms of poems, in terms of stanzas, in terms of representation. This is not new, but using them for a machine learning algorithm to generate beautiful images is something which is commendable in nature. Let us suppose, or let us see how a variational autoencoder encodes a set of images which have different degrees of smile in it. So if you see here, there are four images: a boy, Mona Lisa, and a girl and a man who are laughing. And each of them are basically laughing at a different degrees. So when you extract the feature, whether it is laughing or not, okay, the image is laughing or not, the smile itself, the smileable property of the person itself can be represented using a distribution. So this probability distribution is at the core of the variational autoencoders or autoencoders in general. This is exactly what makes image generation possible. So you take the features. A smile feature is an example. It can also have multiple features. So if you take a single image and see what are the features you can do, it could be a smile, it could be a skin tone, it could be a gender, it could be a beard, it could be glasses, or it could be a hair color. So now when you apply the same to a different type of image, not just for the photographs, you can say, okay, describe my one. So it could say, I have a open space, I have an icon, I have a cloud, I have, like a buildings, I have got an urban landscape, I have got a village landscape, I have an evening landscape, I have a night lights. These are all could be a probabilistic features that are extracted from the image, and each feature will have a distribution associated with it, with the variational autoencoders. Now, these features, the size of these features are representing any image with a suit of the possible parameters is called a latent space representation, where each of the parameters will have either a mean or a variance. So your input images go through a hidden layers, multiple hidden layers for each of the uh, extractions, and it will represent each feature that it makes more important in terms of a mean and a variance. So that is exactly what variational autoencoders do. So now just think these images and auto encode yourselves the features of these images. Now you get idea, isn't it? The guy here, you say long nose, large smile, yellow shirt, and a playful look. The guy here is a confused guy with a questionable expression and harrowing eyes. You can also see a evilish smile on here. The guy in the left, like left bottom, may be called Soma. He may be called as harrowing ears, elevated nose, and a confused look like that. So you understand the concept, isn't it? Like when you go back and go ahead and understand various features in the face, you go ahead and understand the distribution and variance of it. And these variants and distributions are the key to generate the next step of the images. So what you typically do is any autoencoder at up till this point is a non-generative model where you cannot actually generate the images because you encode and decode. But with the variational autoencoders, what you do is instead of saving the absolute values, you save the mean and the variance, and then you give a option to sample from the probability distributions. So when you actually sample from the probabilistic distribution, this variation will start giving you a generative perspective of the VAs or variational autoencoders. So this process is called reparameterization. In the real world domain, you have got mu and epsilon, which will generate you the mean and this variance probability, and then you apply a like a random node there. Instead, what you can do is the z node is transferred, so the equivalent node is transferred, and you add one more epsilon, the configurable parameter or constant in the distribution, and then it becomes suddenly the generative model. Okay, so this is called a reparameterization technique, which is used in the various variational autoencoder. Okay, so this is done in multiple layers. Okay, if you are applying this at a single node or a single feature set, you may have a very limited capabilities to generate a wide variety of models. You may say, I can master the human face manipulation, but I may not master the manipulation of a scenes or an artist. So if you want to have more and more and more features that are predicted through the command or the prompt, the same thing you will have to do, the latent representation, you will have to do in multiple bases. So you create a base, and on the top of it, okay, is there a man? Is there a woman? Is there a child? Is there a boy? Is there a toy? You can go ahead and add them to generate beautiful images. So now, if you see, let's see an example for that. So here you take an image, and if you when you add a smiling vector, the the person in the image goes ahead with a large smile. Similarly, you can subtract the smiling vector also. A smiling photo can be a neutral one. You can add a spectacles or you can remove the spectacles. Okay. So these are the changes when you do the or when you use the reparameterization tech, you will get as a power. So that is how variational autoencoders work. They take your images, first they go ahead and put them into a latent space by doing a encoding and a representation. And whenever you are actually prompting to generate a application or generate a image with the text prompt, they take the features matrices and apply it layer by layer. What is the background? What is the camera angle? What is the proposition? And then generate you the image that you require. So it is also can be used, or it also can be used in a style transfer. Let us suppose you give two images to an algorithm and say, hey, learn the features from the left side algorithm and apply these features of the style of the right and superimpose both of them. You have got a style transfer use case. That is how variational autoencoders, because this is generative in nature, variational autoencoders are very, very useful. So that is how your style transfer use cases happen. Be it a dog that is getting transferred, it has, or be it a portrait, or be it a small child, represented in the artistic style. We all know Ghibli images, isn't it? So with the Ghibli images also, the style transfer is the use case. So you can apply those style transfer and add a lot of image generation capabilities just because of this latent space representation and the way we represent these things in the latent methodology. Okay, this can be done even at a pixel size. And one more use case for these autoencoders is basically the image segmentation and the computer vision. So let us take a use case of a computer vision. Okay, so what you can do is when you apply the latent space extraction to a input of a camera when you are driving, what it can do is it can simply identify the objects on the road, the things on the road, to understand where you are actually going and what you are seeing. So that makes the base for the computer vision, and that will be the base for the driving of the automated cars. So if tomorrow, if we are saying we have a automated cars that are running in the world and they are able to see the roads through the vision, computer vision, on the core of them, autoencoders and the feature extraction power of the autoencoders are working. So that is the level of power autoencoders bring to you. And these autoencoders can reconstruct the things in a very good manner as well. Now that we understand many algorithms are used or can be used in generating the images, none of the single algorithm is perfect in doing it. So the autoregressive algorithms have certain features. GANs have very good features, but the training can be collapsed. It may be stuck in infinite loop of generating similar images because of the decoder or the in the GANs, there is an encoder and there is a discriminator, isn't it? So you can see the GANs in the other video. And here, variational autoencoders, it will only know or generate the applications or images where it understands the feature well. Okay. So there are limitations to everything. Not everything is perfect, but autoencoders and variational autoencoders are a very important piece of the generative algorithm, paradigm. And I hope I explained you variational autoencoders, the working principle of variational autoencoders in a decent way. Thank you all for seeing the video. As usual, follow Medu Yantra and tell it to your friends also. We will bring all the important algorithms of the ML space explained in a simple words to you. If you have any questions, please don't hesitate to comment. We will try our best to answer.